Hello. So we're gonna start trying this out with some videos. This is our first video we're gonna do for hyperbolas, which is our first topic that we haven't covered in class yet. And this is building on to the conic sections from before. So just general notes. There are instructions on Google Classroom and through email that tell you how we're gonna do this online learning phase of our school year and just how to manage all of the stuff through all this craziness and staying at home. Um, this is a time of not something that any of us have prepared for or planned for, and so we're just kind of trying as we go along, and there are probably going to be mistakes that happen along the way. It's probably not going to be perfect, and so as things come up, if there are things that you think of that would be more useful for you and that could help you more, please let me know. And I can add things, change things, do different things to try to make this better for you. In the end, we're trying to make sure that you get the best experience that you can out of this, and anything I can do to help with that would be great to know about, because then I can try to address those concerns. So these videos are fixed videos, right? I'm making these ahead of time. I'm going to send them out to you. As you watch this video, you'll probably have some questions that come up. You can email me those questions. You can text me those questions on Remind. And then either it's a question that it's a problem you're working on, you can take a photo of it, send it to me, or it's an email question, that's fine as well. And then we'll also try doing in a live session, you can bring those questions in, ask me, or I'll just go over some of the common questions that I get. So hyperbolas. This learning target is all about the same thing we did with parabolas and ellipses, now we're doing with hyperbolas. So on the Desmos activity you had, you played around a little bit with some points, looked at the distances, hopefully found a pattern there, and that gives us the definition of the hyperbola. So hyperbola is a shape that looks like this. It can also look like this. And how it's defined is that if we find the two foci on the hyperbola, so like there and there, those are two fixed points. Any point on this hyperbola, if I find the distance from it to the two fixed points, the difference of these distances is constant. So that gives us our definition. A hyperbola is the set of all points, the difference of whose distances to two fixed points, which are the foci, is constant. So now we can come up with the different parts of this hyperbola and then work through its equation. We'll do the parts of the hyperbola on a horizontally oriented hyperbola, and then all of this stuff still applies to a vertically oriented hyperbola. So if I draw in my hyperbola, I'm going to try to draw this big so I have enough space. So you have two curves, right? And then right in the center here, we have the center. And then on the edges of these two curves, those are the vertices of the hyperbola. So each curve, they kind of look like parabolas. They're not exactly hyperbolas, but those curves that look like parabolas, they have vertices just like a parabola has vertices. There's a line that you can draw through the center that connects the two vertices. That's called the transverse axis. And we can label the distance from the center to the vertex, just like on an ellipse, that's the A value. We also have two foci, so I can put a focus over here and a focus on the other side. And the distance from the focus to the center is the C value. just like on an ellipse. Unlike the ellipse, the vertex is closer to the center than the focus is. Right? On the ellipse, the focus was closer. On the hyperbola, the focus is further away. So we have an A value and a C value. We also want to find a B value. And the B value doesn't show up very obviously on this hyperbola, right? Like all of the things we put on here is not actually points on the hyperbola. The B value kind of controls how wide this hyperbola gets. So we're going to go out perpendicularly to the transverse axis from the center. So I'm going to draw a bit that goes out that way and a bit that comes down this way. So I'm going perpendicular to the transverse axis. And that distance is going to be the B value. Now, this line that I drew, that's called the conjugate axis. So it's perpendicular to the transverse axis through the center. But what does this actually mean? Well, if we put the conjugate axis and the transverse axis together, we get side lengths of a rectangle. And so I'm going to draw in that rectangle that has those side lengths. So it has the side length of the transverse axis, so 2A, and the side length of the conjugate axis, so 2B. It gives me that rectangle. And if I draw a diagonal line through the corner, so the diagonal of this rectangle, and then go through the center, notice what this does to my hyperbola. I get the sort of asymptote to the curves of the hyperbola. Right? If I continue this, and continue this, it would follow along that asymptote line, and that gives me asymptotes for this. So that's what the B value does. It controls the width, right? How far wide this hyperbola opens up, because that it controls the asymptote. So if the B value is really tiny, the asymptote would be really steep, and then the hyperbola would squeeze in. If I make a huge B value, then the asymptotes are really wide open, and the hyperbola can go really wide open. I just realized I am moving my hands a lot as I'm saying that, and you can't see me, so that doesn't really help. Hopefully the explanation still helped though. There is some stuff on Desmos you can play around with this on the activity, so you can kind of see how that works as well. So now that we have the parts of this, we have some values labeled in, we can get to the equation of this. So the hyperbola equation looks a lot like the ellipse equation. It's almost exactly the same equation. So I'm going to start off writing the ellipse equation. The only difference, if you think about the definitions, the only difference in the definition between an ellipse and a hyperbola is the ellipse says the sum of the distances to the two fixed points is constant. The hyperbola says the difference of the distances to the two fixed points is constant. Since it says difference, we're going to put a minus sign there. That's the equation of the hyperbola. This particular equation format will give us a horizontally facing hyperbola. And how we know that is because the x term is the positive term. Right, so in this case, in the ellipse, it didn't really matter which one came first because they were both positive. In this case, one is positive and one is negative, and that's going to determine which way the hyperbola opens up. So when it's positive, when the x term is positive, it opens up in the x direction horizontally. If I make the y term positive, keep everything else the same, then it's going to open up in the y direction vertically, because the y term is positive. The a and the b value stay the same. The a is still the distance you go out in each direction to get to the vertex. The b is still the direction you go out in each direction to make that box for your asymptotes. So the size of a and b doesn't matter. In an ellipse, the size of a and b told you the major and minor axis. The bigger one made the major axis, the smaller one made the minor axis. In this case, it's just the positive or the negative. So a could be smaller than b, but a is the positive term number. So kind of see this in examples to see how this works out. So let's do some examples together, and we'll talk about the features of this with that. So starting off with, let's do a problem. let's do something that has a few different things happening in it. So we'll do x minus 2 squared over 16 minus y minus 3 squared over 9 equals 1. We want to find its center. We'll try to find its vertices. We'll find its foci. And we'll write the equations for its asymptotes. So center, that should be the easiest thing we can find on any of these conic sections. It's always that h comma k thing. So I have x minus h and y minus k. Right, so when showing my work for it, I'm going to find all those values that I used to find the center, vertices, foci, and asymptotes. So I know that h is 2, and I know that k is 3, which means my center is 2, 3. Then I need to know my a, b, and c values. So the positive term, that has the a value, which is the 16, so a is 4, b is 3. And to find c, so if we look back at our drawing here, c was bigger here than a and b. In the ellipse, c is smaller and a is bigger. So we look at the biggest value, that gives us our Pythagorean relationship. In this case, c is the biggest value. So c squared is going to equal a squared plus b squared. Unlike an ellipse where a squared equals b squared plus c squared. So I can substitute these values in. C squared equals 16 plus 9, which is 25. So c is 5. And now that I have a and c, I can get my vertices and foci. I know this has the x term that's positive, so it opens up horizontally, which means the vertices and foci change the x value from the center. So for the vertex, I'm going to go 2 plus or minus 4 units to the right and left, and then keep the y value the same. So that gives me 6, 3, and negative 2, 3. For the foci, I add the c value, and that gives me 7, 3, and negative 3, 3. The last thing we need is the asymptote. So if you think about the asymptote on this, right? So I have a hyperbola that's going out that way. Its center is here, and I know that it went out in the right direction 4, and went up 3 to get to that corner point that makes the asymptote. So it goes up 3, right 4. For the other asymptote, it's going to go up 3 and left 4. So the slope, when it's horizontally facing, is b over a plus or minus, because you could go right or left to make the two asymptotes. The equation of it has to pass through the center, so I can do y minus y1, which is the k value, equals our slope, x minus x1, which is the h value. And the slope we know is plus or minus b over a. Typically, you'll see this written with the k value on the other side as well, like that. This is the asymptote equation set up for a horizontally facing hyperbola. So if I plug all the values I know into this equation, I'll get y equals plus or minus b over a, so 3 over 4, x minus 2 plus 3. And that gives me my two asymptotes for this. Let's do one more. So in this one we'll do y minus 1 squared over 1 minus x minus 3 squared over 4 equals 1. We'll do the same thing. Find the center, find the vertices, find the foci, and find the asymptotes. So let's find h and k first. H is with the x, so x minus 3, so h is 3. K is with y, so that's a 1. Center is 3, 1. For the vertices and foci, we need a, b, and c. So we look at the positive term, that's the y term. So a is 1 and b is 2. So notice here that a is smaller than b. That's fine in a hyperbola. In an ellipse, a is always the bigger number because that makes the major axis. In the hyperbola, a is just the direction of the hyperbola. It could be small, it could be big. In this case, it's smaller. C is still the a squared plus b squared. So that's 1 plus 4. It's 5, so c is square root 5. When I'm writing my vertices and foci, I need to know which direction this is opening in. Here the y term is positive, so it opens up vertically, which means the x stays the same, but the y is going to change. So the vertices is going to be 3, is going to be the same, but I add the a value onto the y term. So I get 3, 2, and 3, 0. For the foci, I add it on again, but now I'm adding the c value. So I get 3, 1 plus root 5, and 3, 1 minus root 5. The asymptotes, again, if I think about how this is set up, and my box is here, my center is there. To draw my hyperbola, I had to go up a units, right b units. So now my rise over run for the slope is going to be a over b, not b over a. The equation is similar, right? It's still y minus k slope x minus h. But the slope is different now because a is going up and b is going sideways. You can memorize these cases, but I would say just draw the picture every time because then you don't have to memorize things. You can just look at the picture, right? If I just look at this, I know that a is the one going up and b is the one going to the right. So the slope has to be a over b, not b over a. And so I write this equation. Well, in this case, a over b is 1/2 x minus 3 plus 1. And that would give me my asymptotes for this hyperbola. The last thing we're going to do is write equations for hyperbolas, given some information. So we'll do 2 examples of this as well. So we'll say we have vertices 2, 0, and 6, 0, and foci 0, 0, and 8, 0. And we want to write this equation. So I know that it helps to draw sketches so I can get some idea of which direction it's opening in and some information from that. So I know it has vertices at 2 and 6, 0, and foci at 0 and 8, which means this has to open horizontally. The center has to be right here. So the center I know is 4. So h is 4 and k is 0. And I know that it's going out 2 units in either direction to get to the vertex, which means a is 2. And it's going out 4 units to get to the focus, so c is 4. For the equation, I need the b value. So I can find b by using my c squared equals a squared plus b squared relationship. So I know 16 equals 4 plus b squared, so b squared equals 12, and b equals 2 root 3. From that, I can write the equation now. I know that this is horizontally facing, so the x term comes first, that's positive. So I go x minus 4 squared over a squared, which is 4, minus y minus k squared, k is 0, so this is just y squared, over b squared, which is 12, and that equals 1. That's the equation of this hyperbola. We'll do one more. So we'll say here we have vertices 2, 3, and 2, -3, and the point 0, 5 is on the hyperbola. So we know vertices and we know a point on the hyperbola. So we don't know things that directly give us all the a, b, c, h, k values. But again, we're going to draw a sketch of this because that's usually going to help us. So I go out 2 and I know 3 and -3, those are the 2 vertices of this. If my vertices are on a vertical line, that means this opens up vertically. Right, so my hyperbola looks like this. And I know that the center has to be exactly in the center of these 2 things. So the center is here at 2, 0. And so h is 2, k is 0. I know that I'm going out 3 units to get to the vertex, which means A is 3. But I don't know what B is. But just knowing H, K, and A, I can write most of the equation of the hyperbola. I can, this is vertically opening, so the y term comes first. So I go y minus 0 squared, so just y squared over a squared minus x minus 8 squared, so x minus 2 squared, over b squared. B, I don't know what that is, equals 1. But I do know 0, 5 is on this hyperbola. So I can substitute that point in for x and y, because it has to satisfy this equation if it's on the hyperbola. And now I only have to solve for b squared. So I can start evaluating this. I get 25 over 9 minus 4 over b squared equals 1. I can subtract 25 over 9. So 1 is 9 over 9, so that's negative 16 over 9. And then I can multiply that. Get b squared is 36 over 16, or 9 over 4. I don't really need to solve for b. I can leave it at b squared because my equation just needs b squared. So I write in y squared over 9 minus x minus 2 squared over 9 over 4 equals 1. And that's my hyperbola equation. So we're going to stop this video here. This is all the algebraic stuff with hyperbolas. There's going to be 2 more videos where looking at applications of hyperbolas, and